Hello. So welcome to this last session. We have two talks. So the first one will be by Vedika Khemani. She is an associate professor at Stanford University, and she will talk about topological quantum spin glass ardor and its realization in qLDPC codes.
Okay. Good afternoon, everyone. Thanks very much for the opportunity to speak at this conference for the second time. So, when Abhishek wrote to me to invite me to give a presentation, he asked me to give a historical, or he asked me to give an overview of many-body localization and quantum dynamics. But I am so excited about this work that we posted just last month, very recently, that I couldn't resist the opportunity to tell you about it. I think I'm more excited about this than anything I've worked on in the last several years, at least. And as the youngest speaker in this workshop, I hope you'll forgive me for not giving an overview and instead telling you about this, okay? So the work I'll tell you about is defining a new phase of matter. It's called a topological quantum spin glass. And this phase is going to bring together two very different but very active streams of work that have defined a lot of many-body physics, a lot of activity in many-body physics over the last 50 years or so, but rather independently. The first is the study of spin glasses, and the second is the study of topologically ordered systems. And both of these together really go beyond the Landau paradigm for defining phases of matter at finite temperatures, which has been very powerful in thinking about kind of most finite temperature phases of matter, I would say from magnets to superfluids and superconductors. And in Landau theory, this is a theory of spontaneous symmetry breaking. So you have in mind some system with a symmetry, and the ordered phase, which is there below some critical ordering temperature, is defined by multiple symmetry-broken equilibrium states, which are separated by free energy barriers, okay? And even though, microscopically, to have phases like magnetism or superconductivity, you essentially need quantum mechanics, by the time you describe these phases using Landau theory, the description of the phase is really just in terms of a classical field theory or a classical field which describes some local order parameter in the system. Okay, so for instance, if you have an Ising magnet, then the two symmetry broken states below the ordering temperature are the magnetization up and the magnetization down states, and these don't have the Ising symmetry. The Ising symmetry corresponds to flipping all spins. So these are not invariant under the symmetry, but one of these symmetry-broken states is mapped to the other under the action of the symmetry, okay? The other thing that spontaneous symmetry breaking really gives us, and I'll use this idea of memory to really ground a lot of the discussion of the phases of matter that I'll talk about. So spontaneous symmetry breaking gives you a thermally stable spontaneous symmetry breaking gives you a robust memory for classical information. Okay, so again, in this Ising magnet, this is how a magnetic hard drive works, for instance. I can use this all up state. I have two stable equilibrium states. These two states together define one classical bit of information. So for instance, I could associate the positive magnetization states with the logical bit state 0. This logical bit is the language that Barbara just introduced, and the negative magnetization state is associated with the logical bit state of 1. Okay, and now the fact that my symmetry breaking order is thermally stable means that I encode my information, this one bit of information among these many degrees of freedom. And now, as long as the system is maintained at low enough temperature, even though there's going to be thermal fluctuations, there's going to be some memory of my global magnetization that's going to be preserved, and I can recover my logical bit, my classical bit using that, okay? Now, so this is spontaneous symmetry breaking. There's this very different paradigm for storing memories, okay, which is the subject of spin glasses. So this is a vast subject going back 50 years or so. And the picture you should have in mind when you think of a spin glass, the simplest picture, is a set of magnetic moments. I'm going to denote these again by these Ising spins, which can be in states up or down. And they're all going to be interacting with each other the simplest models or the models over which we have most control in understanding spin glasses are these kind of geometrically non-local or all-to-all type models. So you have these Ising spins, and they're interacting via some interactions, but these interactions can be randomly positive or negative, so the system is very, very frustrated, okay? And as a result of this frustration, the energy landscape in these systems looks very rugged, and it has many, many, many different minima. And the point is that you can associate equilibrium states, stable equilibrium states, with each of these different minima below a certain ordering temperature, which is the glass temperature, okay? The key point here is that these many minima are not related to each other by symmetries. So there's not a description for spin glass order in terms of conventional symmetries that may exist in a spin system. People often use a more enigmatic language of replica symmetry breaking to describe these, but let me not get into that. Okay, so we have many of these equilibrium states not related by symmetries, and each of these, again, can be used to encode some classical memory, and together, the set of all of these different minima can actually encode many, many different classical bits robustly. Okay? So for instance, if you have these different patterns of spins which correspond to states at the bottoms of these different wells, for instance, okay, I can just decide on some encoding scheme where I say, even though I have many, many, many physical bits, I'm going to associate this particular pattern, okay, with a 0, 0, 0 logical state, and this next pattern with a 0, 0, 1, and then 0, 1, 0, and so on. Okay, so once again, the point is, if you have 2 to the k different stable minima, okay, these are not coming from spontaneous symmetry breaking, but if I have 2 to the k stable minima, this gives me a way to encode k logical bits. But right now, once again, this is classical information. Okay, I'm just encoding classical bits. Okay. I should mention here, of course, that a very closely related idea, so Hopfield won the Nobel Prize this year in physics, and his Hopfield network is again a way of having a model with many, many different interactions, which can be used to store different memories. And more generally, the idea, the bottoms can be used to identify different patterns. And the point is that, if you now, for image recognition in an artificial neural network, if you're fed some corrupted version of this pattern, which is like, you're slightly higher up in the well, you have some thermal fluctuations, you can actually find your way down and still recognize that, this is going to be a photo of Phil Anderson, for instance, okay? So most of these minima are not associated with symmetries, and this idea of spin glasses has found widespread application in classical computer science, from machine learning to optimization problems, complexity theory, and so on. Okay. So the second class of systems, which goes fundamentally beyond Landau, is much more quantum. Okay, if I want to think about spin glasses, nowhere there did I have to rely on quantum mechanics or quantum entanglement or any of that. But you might wonder, these are storing classical bits. Can I have a spin glass which stores fundamentally quantum memory, quantum states? Okay, and that's what we're going to be talking about. So to think about how we want to have a quantum memory or to have fundamentally quantum orders, let's turn to this broad topic of topological order. And topologically ordered systems, it's again a vast field, but sort of the best studied ones are gapped systems, okay, gapped topologically ordered systems. So you have some ground state manifold, and this ground state manifold is degenerate as the system size n goes to infinity, and this is separated from the rest of the states by some gap. And crucially, the feature that characterizes topological order is that if you have multiple different ground states, each of these is locally indistinguishable. Okay, so if you look in some local region of the system, you cannot tell whether you're looking at ground state 1 or ground state 2. In other words, there's no local order parameter. Right? This is very different from the Ising magnet, where I could look locally at a patch and see how my spins net up or net down. Okay, here, if you look locally in a patch, you can't tell anything at all. To distinguish between these states, you need to look at some much more non-local operator, which often kind of winds around the system in some topologically non-trivial way. Okay, so the size of the operator that you need to measure or look at in order to distinguish these states goes to infinity as n scales with infinity. That's what it means for these to be locally indistinguishable. And these, to have this locally indistinguishable manifold, this intrinsically comes with a pattern of long-range entanglement. Okay, there's no local order parameter that can tell these states apart, but what we know is that if you start, what this word long-range entanglement means is that if you start with some trivial product state, okay, just some pattern of bits all uncorrelated from each other, and you try to prepare one of these topologically ordered states, the depth, the time for which you need to evolve under some local dynamics actually diverges with system size again. Okay, there's no kind of locally correlated description of these topologically ordered states. So quantum entanglement is fundamentally important in describing such states. Okay, what's neat is that the same feature of local indistinguishability is also corresponds that we use to define topological order also corresponds to what are called the nil-Laflamme conditions in error correction. And again, building on Barbara's talk, the point is if you need some large operator whose size diverges with system size to tell these states apart, well, then that operator, the size of that operator defines this thing called the code distance, which Barbara mentioned, and you can use these any set of locally indistinguishable states can be used to encode logical qubits. Okay, and these logical qubits, again, remember, I want to be able to preserve both bit flip and phase flip information, so I really want to have no way of locally telling you which state you're in. Okay, good. So far, for this example of the 2D toric code, I just told you that the ground state can encode these logical qubits, but you want it to be robust, okay? You want it, again, to be a memory. And it turns out that if you want a thermally stable quantum memory or a thermally stable topological order, then you need to go to higher spatial dimensions, okay? We know that we need to go to dimensions at least greater than 2. Whether you can do it in dimensions 3 or not is an open question as far as I know. But for toric code and various other known models, you have to go to dimensions at least 4 in order to get some thermally stable encoding of your logical qubits, which can then again be robust in terms of having some finite temperature state, which is topologically ordered. Okay. So, these are the 3 kind of big classes of phases of matter that I've presented to you so far. Classical memory, which can be encoded with spontaneous symmetry breaking or with spin glass order, and quantum memory, which requires topological order. And the phase that I want to discuss today is a topological quantum spin glass, which is characterized by this rugged energy landscape. But now, the state in every one of these wells, there's a stable state in every one of these wells, whose lifetime is infinite in the infinite size limit, but the state of each of these wells is a highly entangled state. There's no classical description of it. So this is a phase where even though you're at finite temperatures, you intrinsically need quantum entanglement and a quantum description in order to capture the properties of this phase. Okay. So the pictures that I'll be telling you that I'll be showing you will be fairly qualitative, but I just want to emphasize here that the results that I'll be presenting are rigorous. There's a theorem that we prove, and actually even for models of spin glasses that have been studied for 50 years now, results that are this clean and this rigorous, I've at least found it hard to find in the literature. Okay, so I'm going to be proving these various statements and what defines this topological quantum spin glass. Okay, there's some features of it which have to do with the classical complexity of the free energy landscape, the fact that you have so many different minima. That means that I want to define this by a property called shattering. That means that exponentially many stable minima. Okay, and actually most of these minima don't contain ground states of the system. So most of the minima are associated with highly excited finite energy density states. Okay, so this is a classical feature. And then I also want to, in the phase that we'll talk about, there's also a quantum complexity associated with these equilibrium Gibbs states, which is to say that each of these minima is associated with a highly entangled topologically trivial mixed state. And the system actually has not just one, but many embedded quantum memories in its landscape. Okay, and for the experts, the types of models that these are quantum LDPC codes with strong enough linear confinement, non-redundant checks, and constant code rate. Okay, but let me give a more qualitative picture for what these models look like. Okay, so these models are going to live on what are called expander graphs. Okay, so you can visualize an expander graph as something where it has a locally tree-like geometry here, but then the boundaries are closed. Okay, so it's like you can think of some Bethe lattice if you want, but then everything is closed up on itself. And these models have the property that the boundary of any subset of sites is proportional to the volume. Okay, so it's saying if you cut out any chunk of sites here and you look at how big its neighborhood is, well, the neighborhood is going to scale proportionally, the size of the boundary will scale proportionally to the size of the bulk. Okay, so that's the defining feature of these graphs. You can define these classical low-density parity check codes on these graphs. All this means is that you have a model that's actually local on this graph. Okay, so every check, which is just some generalized Ising interaction, which is some product of spins, which can be more than 2. It can be 2, 4, 5, whatever you want, as long as it's finite and doesn't scale with n. So it's just a it's just a set of these types of interactions, and those interactions are local on the graph. My bits live on the edges of the graph, and the vertices have some sets of interactions which involve the bits that are adjacent to it. And LDPC means that every check involves finitely many qubits, and also that every bit here is part of only finitely many checks. Okay, so it's not all to all, because every bit is only part of finitely many checks. On these particular geometries, you can get what are called good codes. And these are codes which are kind of the most robust, the most efficient codes that exist. Okay, so if you have a code, you want to pack in as many logical qubits as you can for a fixed overhead of physical qubits. And you want these logical qubits to be as robust as possible. Okay, so that means that for a fixed system size, which is the number of physical qubits, you want to see how does the number of logical bits, which is k, scale with n, and how does the code distance, which is how different are these ground states, how robust is your encoding, how does that scale with n? And in a good code, k and d both scale proportionally to n, and good classical codes have been known for many, many decades. Okay? The really exciting thing over the last few years is that you can start from these types of classical LDPC codes and take some very special products of these codes. Okay, a product you can visualize as a way of building up some kind of higher dimensional manifold from a lower dimensional one. So if I take a product of 2 lines, I can get a plane. Okay, so likewise, or if I take a product of 2 circles, I can get a torus. So here, you can take a product of these 2 an expander graph and another expander graph, which is locally tree-like, and construct what's called a higher dimensional expander, which still has some expansion feature, but now you see that you have many of these local plaquette-like objects that you've created in there. Okay? And in these high dimensional expanders, you can define quantum LDPC codes, which have both X and Z type interactions or stabilizers or parity checks, which will all commute with each other. And these, once again, will give you ground states which are now locally indistinguishable, and they can give you ground states which are locally indistinguishable with these kind of optimal coding parameters here. Okay, and the fact that you could get these is, again, a very, very recent development just in the last 2 or 3 years. Okay, good. So the point is that there's a connection between classical LDPC codes and spin glass order that has actually been appreciated by people working in spin glasses for quite a few years. And they've studied various kind of random families of spin glass models and made a connection with spin glass order. But we'll be using a property of these codes called linear confinement to argue much more directly for spin glass order, and to actually argue for spin glass order in a much, much wider class of classical models even. And then, as I said, you can take products of these to get these quantum LDPC codes, which will inherit this confinement property that I'll discuss. And these are the models that give you this topological quantum spin glass order. Okay? So I want to make a few comments here. The models that we'll be talking about have no disorder at all, or they can have no disorder at all. Okay, not in the interaction geometries, not in the couplings, nothing. Conventionally, models of spin glasses have disorder at least in the geometry or in the strength of the interactions. Okay? So given that we have no disorder whatsoever, this adds to the family of known spin glasses, even in the classical context, and might give us some insight into structural glasses like window glass, which again have this glassy behavior, are thought to have the glassy behavior due to some geometric origin rather than due to frustrations in interactions. Our models are frustration-free. Okay? Second, our method of analysis is completely rigorous. It relies on properties from codes rather than replica symmetry breaking. And at least to me, this is much more transparent in understanding what the spin glass behavior is doing, or what the spin glass order is. You know, these expander graphs might seem artificial to many of you, and that's true, but you know, just historically, these have been very useful in the analysis of many statistical mechanics problems. For instance, you know, if you're doing StatMech on the Bethe lattice, even in the study of spin glasses, more geometrically non-local models have played a very important role in getting to the understanding that we have of these models. And much as in those problems, we expect, or rather hope, that some of the phenomenology that we find in these models might persist to local Euclidean models with high enough dimensions. So that's one point. But you know, we're also entering this age where artificial or synthetic quantum systems are giving us access to much wider classes of models than what nature gives us, which you know is three spatial dimensions and Euclidean spaces. So given that these geometries are now accessible in these engineered systems, you know, whether they're neutral atoms or kind of non-local cavity systems, which allow you to engineer different types of interactions, it's now more physical as a many-body physicist to start asking about the physics of these models in these different settings. Okay. So a couple of other points. When viewed as codes, as I was mentioning, these models have k proportional to n. So that means they encode a number of logical qubits, which is proportional to the number of physical bits. So this corresponds to an exponentially large ground state degeneracy or extensive ground state entropy. Okay? Given these are ground states of the problem, these are actually related by sort of generalized symmetries. Okay, so if you're talking about quantum models, these are the logical operators of the code. Those can be viewed as higher form symmetries or deformable symmetries, but the many different ground states are related by symmetries, and you already have exponentially many of them. So that already points to this extensive ground state entropy already points to something quite unusual happening in the system. And actually, in a separate paper, we proved that if you have models in these codes, which are gapped with some ground state degeneracy, even if it's exponential, then those features are provably robust to adding weak graph local perturbations. Okay, so this is not some artifact of a fine-tuned point. Okay, what's also known from the coding literature is that these models can act as passive memories. Okay, so they have local decoders. You can think of a local decoder as just some local Monte Carlo dynamics, or you couple your system to some local bath, which cools you to some low enough temperature. These models are known to have local decoders for information that is protected in the ground states. And conventionally, these local decoders are usually associated with thermally stable order. For instance, in the 2D Ising magnet, you have thermally stable ferromagnetic order, or in the 4D toric code, you have thermally stable topological order. But intriguingly, what's known is that, and that was pointed out in the quantum context by this recent paper by Andy Lucas's group, is that even though these models have local decoders, the partition function is actually analytic at all temperatures. Okay, so it's these very weird properties of these models, and almost every other, or actually maybe every other model of some asymptotic code that we know corresponds to some non-trivial phase of matter. Okay, so this prompted us to ask, what is the physics of these LDPC codes? Okay, you have these intriguing properties when you view them as codes, but these features are coming from some physical features of the problem which define some type of phase. So what is the physics, or what is the phase of these LDPC codes? Okay, so the plan, very briefly, is to tell you how we do this. Okay, so I've given you the pictures for what the phenomenology is. But I'll tell you a little bit on how we define these different Gibbs states components in the system. Because you have many, many equilibrium states. How do you define that mathematically if you want to prove some theorem? And then how do you use this feature of codes to derive spin glass order? And then, how do we talk about this other feature of topological order in the nature of the Gibbs states? Okay, so defining distinct Gibbs states components. Okay, so if you don't think too hard, and I ask you, how do you want to define a non-trivial finite temperature phase of matter? You'll probably tell me a non-trivial finite temperature phase is one in which the Gibbs state ceases to be unique, or one where you have multiple different equilibrium states at some finite temperature. Like in a 2D magnet, you have the all-up state and the all-down state, both of which are equilibrium states. Okay, but if you just look at the Gibbs state, the global Gibbs state, which is e to the minus beta h, this is fully symmetric because the Hamiltonian is symmetric, and it's a unique symmetric state. So what does it mean to have these many, many components? Well, there's a large literature on this question in classical statistical mechanics in the subject of spontaneous symmetry breaking. And you can do various things. For instance, you can try to add different boundary conditions to your system, and you can ask, if you take the system size to infinity, there's some ball in the middle of the system. Is it sensitive to what boundary conditions you put in? Or there's some various mathematical axiomatic definitions directly in the thermodynamic limit by Dobrusch and Lanford and Ruel. Okay, so but the picture that I want to present to you is a little bit different from these. Okay, so let's look at this picture. It's very transparent, I think. So you have this global Gibbs state. Okay, let's map out this Gibbs state, and here the picture that I've drawn is for a Gibbs state that's a low enough temperature. Okay, so let me map out this Gibbs state in configuration space and say that I have some regions where my Gibbs state has high weight. Those are colored blue here, okay? And I've denoted them as plus and minus. And these regions where the Gibbs state has high weight is surrounded by other configurations which have low weight, okay? And the relative weight of these different components in the Gibbs state can be quantified by this quantity, which I'm calling the bottleneck ratio. So let me look at one thing which I'm going to call a component here, okay? And I'm going to look at the ratio of the weight in the Gibbs state of the boundary surrounding that component. And the boundary is something that I choose, okay? I can choose to decide which configurations I want to put in the boundary. So I'll look at the weight of the boundary relative to the weight in the bulk, okay? And this is, of course, the ratio of the free energies in the boundary and the bulk because it's the weight in the Gibbs state. So if this bottleneck ratio goes to 0, which means you have 0 weight in this bottleneck relative to the bulk as n goes to infinity, this formally defines for you a free energy barrier in the system, okay? And now, if you have some local dynamics, some local detailed balance obeying Markov chain dynamics, Markov chain Monte Carlo, that prepares the Gibbs state for you, the global Gibbs state for you as a steady state, then you can rely on what's called the Markov chain bottleneck theorem to show that if you end up, if you start with your state in one of these components and your local dynamics has to go through the bottleneck in order to escape the component. No matter what you do to leave it, you have to go through this bottleneck region. Well, then you can show that the memory, if you start off here, the time for which you remain in this component diverges goes to infinity with increasing system size, and it actually diverges as the inverse of this bottleneck ratio delta. Okay, so when your configuration space, when the Gibbs state, the global equilibrium Gibbs state, has this feature, so in an Ising model at low enough temperatures, these two blobs correspond to global magnetization above some threshold and global magnetization below some negative threshold. Okay, and you can show that there would be these bottlenecks, but then the system retains memory here. Okay, so the non-trivial phase that we're talking about is that, well, you can get different Gibbs state components by simply truncating. Okay, you say that you have this bottleneck, but the ratio of the weight in the bottleneck to the weight in your system is going to 0 anyway, so you might as well just truncate and forget that you had this larger space, because if you start off here, you're really never going to go access that. Okay, so you truncate to a given component, and if you have many different components, each with some weight, then this defines a non-trivial phase for you. Okay, and then just jargon is extremal components are those which cannot be further subdivided. So now with this, there's a very clear definition of a classical spin glass. You want to say that you have exponentially many Gibbs state components, which are these bottlenecked subsets of configuration space, which are not going to be related to each other by symmetries. You want to demand that every single Gibbs state component has exponentially small weight and diverging lifetime. And there's this feature called incongruence, borrowing some terminology from Hughes and Fisher, which actually says that most of these Gibbs state components only contain finite energy density states, and in fact, they don't locally look like ground states anywhere in the system, okay? So given this, the other thing you can show is that steady states of local detail balance obeying Markov dynamics form a convex set. This is a known fact, and every steady state can be written in this form, which is just a weight, a probabilistic average, not superposition, but just a linear combination of different such extremal Gibbs state components. And given some number n of these extremal Gibbs state components, you basically have a probability vector, which is what is the probability of being in a given component. And under your dynamics, this n-dimensional probability vector is fully conserved, which means that your system has a classical memory which encodes k equals log n bits. Okay, so this is classical spin glasses, and much of what we did kind of analytically using these code properties is to derive that you have these types of bottlenecked sets. Okay. So now moving on to, oh yeah, okay, sorry, okay, good. So now I want to talk about a quantum bottleneck theorem. Yeah, 3 minutes, oh, shit. Oh, okay, all right. Okay, I guess I'm not going to talk about much of anything. Okay, sorry. Okay, so for a quantum bottleneck theorem, instead of configuration space, I have Hilbert space, okay, and I want to imagine some local quantum channel which again, has to go through some bottleneck region. You can think of some local Krauss operators that has to go through some bottleneck region to go from part one to escape part one. And you can actually generalize. You can come up with a quantum version of a bottleneck theorem, which we proved. And this is weaker than the classical bottleneck theorem. There's a square root here because you have to take into account the probability of tunneling between these different states. And you also, the proof of the classical bottleneck theorem, there's just a sum over paths. But here, your quantum generalization is not direct because you have to worry about interference effects and so on, and off-diagonal components between V and the bottleneck. Anyway, we did all of this, and we got this quantum bottleneck theorem, which we can now use to define quantum subspaces, okay? And I should say here that the existence of this channel which prepares a global Gibbs state, a local channel which prepares this, is actually also a very, very recent result just in the last year or so. Okay, so now we have some statements to make about such channels. Okay, so we know how to define these many different Gibbs states, how to talk about these bottlenecks, okay? Now I want to say what would it mean for these states to have quantum memory. Okay, remember in the classical context, there's this classical probability vector which is telling you how much weight you have in these different components, and that's your encoded classical information, okay? How much weight do you have in these different wells? So what does that mean in the quantum context? So let's again go back to the toric code. Okay, so we have this model that Barbara discussed. It's got these commuting stabilizers. It has 4 different ground states. So it encodes 2 logical qubits. I can write these as up, 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 down, down, up, down, down, okay? And these states, again, differ in this kind of non-local operator. This non-local operator, or this logical Z operator, is what in condensed matter is known as this Wilson loop operator. This is an operator that commutes with this Hamiltonian. So you can think of it as a kind of symmetry, but actually you can multiply it with any stabilizer and it remains a symmetry, so it's a deformable symmetry of the Hamiltonian, and the model also has these deformable X symmetries, okay? So now I have this choice, okay? I wrote my ground states here in this logical Z basis, but I'm supposed to be able to preserve any logical quantum state. So I could have also written it in the logical X basis or the logical Y basis or anywhere else pointing on some multidimensional block sphere for my logical qubits. Okay? So as I said, my 2D toric code is not thermally stable, but let me just go to 4D. And the picture is the same. You have some logical qubit states. Those correspond to eigenstates of very non-local operators, which commute with all the parity checks in your Hamiltonian. Okay? And now you can define any possible logical state for your qubits. If that's supposed to be thermally stable, well, then that implies that every single steady state of you have many, many different steady states, and every possible steady state of the dynamics has this particular form if it's to be a quantum memory. It looks like a tensor product between this density matrix mu, okay, and this mu is some 2 to the k by 2 to the k density matrix, which encodes the logical state. And alpha is the state of that logical space. Okay, so it's telling me which logical state I'm in. Those correspond to different density matrix, whereas the rest is the sigma, and that's the same for all possible states that I'm talking about. So that's the rest of the Hilbert space, the syndrome space. Okay, so the point is that different pure states correspond to different pure states from mu, correspond to, you now have this continuum of steady states corresponding to rotating your logical qubit on the block sphere, okay? And these are all non-orthogonal extremal states, and your quantum memory kind of takes this form, okay? So now I'm out of time, so what I want to just flash for you in 1 minute is you have a feature of these expander graphs, okay, which makes it very, very hard to make excitations. If you have an excitation, you start with a ground state, you start flipping some qubits, you encounter very, very large energy barriers in the system. Okay, so we can use these types of linear energy barriers. That's what we use to derive bottlenecks and linear free energy barriers. Okay, so it's coming from a very controlled understanding of the energy landscape in these codes. That's what's behind showing that you have these bottlenecked subspaces. And then we can do a simple kind of counting argument to say that I have many, many bottleneck subspaces. So that's the measure of the classical arguments. And really, if I had like 5 minutes, I could just do this for you directly, which should be contrasted to anyone who's looked at any paper on replica symmetry breaking. It's just counting, it's just linear algebra. It's so transparent. And it's just like, yeah, you have energy barriers, you have free energy barriers, and these carry very little weight. Okay? You can do this for quantum models with a little bit more work. You can actually do numerics that shows you kind of different dynamics for heating and cooling and hysteresis, and you know, you get like this kind of what the landscape of Gibbs states look like. You can understand that. Okay? And these are these classical features. And now, in the last second, you know, if you're talking about these topological quantum models, the point is you have all of these different logical sectors, and you can embed quantum memories into each of these, you know, using a well and its symmetry-related copies. You actually can't use the full set of all wells to define your quantum memory, because you can distinguish between the wells by just measuring energy. But you can take a given well and then its partners and embed a quantum memory, even at finite energy density. And you can do these for the ground states, of course. So there's many, many embedded quantum memories, and you have kind of a mixed quantum classical memory here, unlike a pure quantum or a pure classical that I told you about earlier. And each of these states, in any one subspace which is bottlenecked, you can show that these bottleneck subspaces are long-range entangled Gibbs states, that there's no short-range entangled decomposition of these. And moreover, if you pick any state from one of these subspaces, you can actually, it's a stronger form of topological order, what people often refer to as NLTS, or no low temperature trivial states. You can show that these Gibbs states are actually very, very, very highly entangled. Okay, so I'll just leave this as a kind of summary slide for the different features that these models have. Thanks. Sorry for going over.
Time for a couple of questions.
Yeah. So Well, I will try to understand the topological order in this quantum LDPC code. Um, so I wonder how much of the expander graph structure I really need. So perhaps one way to get at that question is to ask about the structure of the one-form symmetries.
Can't hear you too well, sorry.
I mean, the structure of the one-form symmetries that you
Yes.
have in the...
Yeah.
So do you have an infinite number of one-form symmetries?
Yeah, so we have infinite number of one-form symmetries, but actually like most of the Gibbs states that we're talking about, the one-form symmetries give you all the ground states.
That's right.
But most of these, like if you look here, the one-form symmetry takes you from this sector to this other sector, but even within a sector, you have exponentially many states, and that's not coming from one.
Right.
Yeah.
I understand.
Yeah.
But for capturing the entanglement structure,
Yeah.
the structure of the one-form symmetries that matters. It will take you across these different structures. So what is that structure? Are there multiple one-form symmetries?
Yes, there's there's not exponential, there's order n one-form symmetries.
And they have anomalies with each other?
They have what?
They have mixed anomalies?
I don't know.
I presume they do. So anyway, there is some mathematical structure there which...
Yes.
But seems to me that may not depend on... I mean,
So,
the graph is taken out of the picture.
So Fracton models, also have many one-form symmetries. So this is kind of a version of that, but now with thermal stability, which those models don't have, and with this extra feature of that we're not just talking about the ground states, but we're also talking about all of these other landscapes. But the fact that you have a number of one-form symmetries, which is increasing with system size, is not so unrelated to what you see in Fractons. Yeah.
Okay.
Yeah. Sorry, I missed something very basic. So in the expander graph the model is defined on that, you said there was no frustration.
Yes.
Right. So what gives rise to the multiple minimum structure? That's one question. And the second quick addition is so in terms of having the memory of the capacity, you mentioned, does the system need to have a finite complexity, or it's in the Sherrington-Kirkpatrick class?
Okay, so for the first question, it's not frustrated because you have these ground states, and in fact you have exponentially many ground states which satisfy all of your checks. But the reason you have so many others is that if you want to make just one little violation somewhere of one check, so you suppose you want energy 1, there's no kind of local way, you want to change this thing locally, but if you try to change something locally on the expander graph, you make more energy, so you have to actually change it very, very globally before you can come back to having just a local excitation somewhere. So it's that geometric kind of frustration that's giving you all of these extra minima. Then you asked something about Sherrington-Kirkpatrick and complexity. So here it's one-step replica symmetry breaking in the classical case, not this multi-step that Sherrington-Kirkpatrick has. And all our energy barriers are kind of linear and extensive, and in Sherrington-Kirkpatrick you have like a much more hierarchical structure there.
I think we are running behind time. I'll just...
Very quick question following up on Sentinels. The perturbations, you said these things were stable too, which are local on the expander.
Yeah.
Do they have to respect the one-form symmetries or microscopic, or they're emergent?
No, they're emergent symmetries. So the point is that I start with all of these different ground states, but then I can perturb the model generically. And the point is that the ground state degeneracy is preserved. Okay, so you get these emergent one-form symmetries and everything kind of continues that way. Yeah.
Yeah, so there's still some time after the session ends till the banquet, so you can corner Vedika and ask. Many of you have many more questions I can see. Thanks, Vedika.